Oh, okay. Welcome back, welcome back, welcome back. This problem was nothing short of a long process in learning, and I see why that the scientists do what they do with this setup. But this uses a technique that we talked about quite a long time ago, I believe in 31. Um, that being said, the application, like I said, in that question is not pretty, or for this question is not necessarily the prettiest. Um, but it is definitely something that needs to be understood if we wish to continue our journey in the things of physics. Like I said, long, tedious learning curve. Let's dive in and see if we can tackle it. The statement reads, calculate the threshold, aka the minimum momentum the pion must have in order for the process pi plus p goes to kappa plus sigma to occur. The proton p is initially at rest. Use m pi c squared equal 150 with mp c squared equal 900 and mk c squared 500, m sigma c squared equal 1200, all in mega electron volts. Hint: formulate the threshold condition. Examine the collision in the center of mass or center of momentum frame. This center of momentum frame, remember, very, 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 very interesting to deal with. Okay, remember what the condition was for it. That the center of mass, the center of momentum, showed that the collection of momentum was zero. Let's draw it out. So what we have in our normal situation is that we have the pion hitting the proton, and that we're going to get the kappa and sigma stuck together moving to the right. However, in the transform frame, what we see over here, before the center of mass tells us that not only is the pion moving, but the proton's moving opposite to where we cancel out the momentum. Because remember, the center of momentum frame has to be zero. And then what we have is a zero momentum here. The difference is we have to use relativity to transform from our classical understanding into the relativistic regime, and that's where the trouble comes in this gigantic mess of a problem. So let's go ahead and move on with our discovery of how to deal with this. All right, so as I kind of just ranted about, if we reframe this in the center of mass frame, which requires total momentum be zero, this threshold occurs when the incident energy is just sufficient enough to cover the rest energy of the resulting particles with none, quote, wasted as kinetic energy. Momentum would mean that, momentum would mean that momentum exists because of kinetic energy. Thus, in the lab, we want the kappa and sigma to have the same velocity at threshold, and this threshold works because of the invariance that we saw when we had e squared minus c squared p squared equal bar e squared minus c squared p squared. So again, the energy momentum was invariant, and now we get to use invariant to our advantage, but the invariance has to happen in the setup of the transformation, meaning that the lab scenario has to equal the center of mass frame scenario. This tells us that the center of mass, which again by definition, or center of momentum frame, has to be zero momentum. So that's the advantage of working in these invariant frameworks, and it is such a pain to get us there, and it's going to take a lot of writing, and what we're going to see might scare people, but really it's just a bunch of paperwork, and if you put it in Mathematica, it's not as bad, but we're running out of space, so let's see what it is. All right. So with these two systems, we have a before and after to consider with both energy and momentum. With the threshold EI equal EF bar, since we are trying to just overcome the rest energy. So let's see what we have. E bar center of momentum equal EF equal to MK C squared plus M sigma C squared. Both of them have C squared factored out. Similarly, this threshold requires EI equal EF in the untransformed frame and PI equal PF with the same velocity. So the lab frame momentum needs to equal the p of pi, the pion, the proton, and of course the proton in the lab frame was at rest, so that goes to 0, so we're just left with the pion momentum. And the energy of the lab was the energy initial, but note that we only had a rest mass for the proton, that's what this term is, and we had the whole energy here with the kinetic and rest mass terms. So we're good here. This all looks fine. Now the hard part is making sure that everything is equal in terms of making sure the invariant statements are computationally accurate. That being said, oh, it looks like my E didn't cancel down. My apologies for this one. I don't know why they didn't cancel or copy down. That being said, here's our algebraic statement now, and we simply need to work our way down on it. That should be an M there, and I don't know why the M didn't paste. But we see we get a couple cancellations after we FOIL it out and cancel it with this thing over here. So, you know, we got a lot of cleanup to do, and let's see what we can do with that cleanup. All right, so we're still cleaning it up. We're putting it in position to get rid of some C4s, C to the 4th powers rather. And then you see we just have a bunch of masses here, squares and square roots, and we just simply have to continue cleaning up. Again, not an easy process to deal with, quite annoying actually. But after we deal with all the algebra canceling down and all of this nitpickiness, what we see is that we have everything as far as the equivalent statements with the masses on the right hand side, given that we have m, p, and the momentum of the pion here, and we could put both of those in for what we have is equal to the square root of all these masses and their different combinations. Again, I'm talking over a large part of the work, but I think you could see the work just needs to be siphoned through and a lot of algebra needs to be taken into account. So take as much time as you need to with that. I'm going to move on for the sake of timing. That being said, we could solve this explicitly for the momentum of the pion by multiplying that other thing over, and we see this is exactly what we wanted. However, we note the masses were given in terms of mega electron volts, so that tells us we have to divide by the c squared term. And at this point, I have no curiosity to want to plug it all in my calculator. So I said nope, and I used Mathematica and a couple other shorthand tricks to tidy this up. That being said, once we do all that, we get that the momentum for this pion is equal to 1133 mega electron volts per C. And the reason why we have to have this threshold here is because we simply need the reaction to happen. Again, the advantageous part of this setup is that it allows us to have the invariant statement hold, which gives us a gateway into more conservation laws. So it helps us to have another problem solving method. I believe we have another energy style question like this, so we'll definitely see it again. But boy, is this not, I mean, this is fascinating, don't get me wrong, but boy, is this a headache. Because not only do you have to deal with conservations, but you also have to deal with the invariants. So conservation meets the invariant statement, and that is a wonderful and a big thing to keep organized. So if you have any other articles or practice with these, please comment below and let us know. But this is, I've seen some other particle physics, nuclear physics books, and this kind of concept is not going to leave us in physics. So with that being said, I'll see you at the next one.